Hello friends, I welcome you in lecture number 18 on complex differentiation. In lecture number 17, we have understood what is harmonic conjugate and we have seen how we can find out harmonic conjugate of a given harmonic function. In this lecture also, we will discuss one more problem on finding the harmonic conjugate of a given complex function. So we consider this example. Here we have to first prove that this function 2x minus x cube plus 3xy square is harmonic in some domain, and then we have to find its harmonic conjugate. So first we prove that given function is harmonic in some domain. Given function is u equal to 2x minus x cube plus 3xy square. And to prove that this is harmonic, first we will require first and second order partial derivatives of u. If we differentiate with respect to x, then we have derivative of 2x is 2 minus derivative of x cube is 3x square, and here 3y square is constant and derivative of x is 1. Similarly, del u by del y equal to, this is independent of y, and we consider x as constant when we differentiate with respect to y. So derivative of this is 0 with respect to y, and here 3x is constant and derivative of y square is 2y. So we have del u by del y equal to 6xy, and then we require second order partial derivatives. So to obtain del square u by del x square, we differentiate del u by del x with respect to x. So derivative of 2 is 0. Here we have minus 3 into 2x, that is minus 6x, and derivative of 3y square is 0 because we consider y as constant when we differentiate with respect to x. Similarly, we require del square u by del x del y, that we can obtain from this by differentiating with respect to y. So again this is going to be 0 when we differentiate with respect to y, and here 3 constant, derivative of y square is 2y, so it is 6 into y. This we can obtain from this also by differentiating del u by del y with respect to x. If we differentiate this with respect to x, 6y is constant and derivative of x is 1, so we get the same answer. And we require del square u by del y square, that is derivative of this with respect to y. So 6x becomes constant and derivative of y is 1. And now we can observe that all these first and second order partial derivatives are polynomials in variables x and y. So they are continuous at every point in the complex plane. So we write that clearly: del u by del x, del u by del y, del square u by del x square, del square u by del x del y, and del square u by del y square are continuous in the complex plane. Continuous in the complex plane or in the plane. And second condition is we have to check whether u satisfies Laplace equation, that is we have to add del square u by del x square and del square u by del y square. Del square u by del x square is minus 6x and this is plus 6x, so this is going to be 0 at every point in the complex plane. So this condition is also satisfied. So our domain is complex plane in which this function is harmonic. Therefore u xy is harmonic in the complex plane. Harmonic in the complex plane or in the xy plane. So we have proved first part of the question, so that u is harmonic in some domain. Here we find that u is harmonic in the whole complex plane, and now we try to find out harmonic conjugate of u. So for that we first assume that suppose v is harmonic conjugate of given function u. So we write that let Vxy be harmonic conjugate of uxy in the complex plane, or we write simply in the plane. And therefore by definition, if we write this function whose real part is u and imaginary part is v, then by definition this function is analytic in the plane. We know that v is harmonic conjugate of u if u plus iv is analytic, and if u plus iv is analytic, then u plus iv is differentiable. Therefore u and v will satisfy Cauchy-Riemann equations del u by del x equal to del v by del y and del u by del y equal to minus del v by del x in the complex plane. So I am not writing every time that these equations are satisfied in the complex plane. Now we are having partial derivatives of u with respect to x and y, that we will substitute here, and we will have partial derivatives of v with respect to x and y. What is del u by del x? It is 2 minus 3x square plus 3y square. 2 minus, let me check again, 2 minus 3x square plus 3y square. 2 minus 3x square plus 3y square, that is equal to del v by del y, and del u by del y is 6 into xy. So here we write 6xy equal to minus del v by del x, and this we can rewrite in this way: del v by del y is 2 minus 3x square plus 3y square. We give this number 1, we are going to use them to obtain function v, and del v by del x can be rewritten as minus 6xy, and we give this number 2. So we have obtained first order partial derivatives of v with respect to x and y, and using them we will obtain function v, which is our harmonic conjugate. Now as we have discussed in previous lecture, that either we can use equation number 1 or equation number 2 to obtain function v. So suppose we integrate equation number 2. We know that differentiation and integration are reverse processes of each other or inverse processes of each other. So if we want to obtain function from its derivative, then we have to integrate the derivative with respect to that variable. But here derivatives are partial derivatives. Here we have del v by del x. So if I want to obtain v from this equation, I have to integrate this del v by del x with respect to x partially, that is considering y as constant. And if I want to use this equation first, then I have to integrate del v by del y partially with respect to y, and at that time we consider x as constant. Suppose we use equation number 2, then I have to integrate equation 2 with respect to x. Integrating 2, we can write partially also, partially with respect to x. That will make the sense clear that we consider y as constant. So on the left hand side I am writing del v by del x integral with respect to x equal to minus, and we are integrating with respect to x, so minus 6y is constant, and we will integrate x with respect to x, and whatever constant term will be there, that may include y terms also. So instead of writing arbitrary constant, we will write arbitrary function of y, because we are integrating partially with respect to x. Therefore y is considered as constant. So whatever terms are there, which includes constants and y only, they will be treated as constant. So instead of writing arbitrary constant c, we are writing arbitrary function of y. And now here we will have v, integral of del v by del x with respect to x is function v, and here we have minus 6y, and integral of x is x square by 2, so we can get 2 cancel with this, and here we can write minus 3y into x square plus g of y, and this is equation number 3. Here we don't know what is this function g of y, so to obtain this function we will use another partial derivative of v, that is del v by del y. Now we can use this del v by del y to find out the value of g of y, and to use this equation first I will require del v by del y. So I differentiate equation number 3 partially with respect to y. Differentiate 3 partially with respect to y. We have del v by del y equal to, we consider this x as constant, so minus 3x square here becomes constant, derivative of y is 1, and here g is function of y only, therefore we have ordinary derivative of g with respect to y. And now we write value of del v by del y from equation number 1, which is 2 minus 3x square plus 3y square. This is 2 minus 3x square plus 3y square, and here we have minus 3x square plus derivative of g with respect to y, and we have written del v by del y from equation number 1. So in the bracket we mention that using equation number 1. Now we require dg by dy, so we transfer this on right hand side, so that will cancel this minus 3x square, and we will have dg by dy equal to 2 plus 3y square, and this is function of y. And if we integrate both sides with respect to y, we have integral of derivative of g with respect to y equal to integral of 2 plus 3y square with respect to y, and plus arbitrary constant. Now here we have functions of y only on both sides, therefore we write arbitrary constant c here, and integral of derivative is function itself by the fundamental theorem of calculus. Here integral of 2 is 2y plus, here 3 is constant, integral of y square is y cube by 3, that will get 3 cancel, and plus c. So this is our g of y that we substitute in equation number 3, or we can directly write, therefore using this equation 3 becomes, now we have function v on the left hand side, and here we have minus 3y into x square, or we can write minus 3x square y, and g of y is plus 2y plus y cube plus c, and here c is arbitrary constant, where c is arbitrary constant, and this is our required harmonic conjugate. V is harmonic conjugate of given function u, and we can easily obtain it using this method. What we have done is we have just used the definition of harmonic conjugate. We know that V is harmonic conjugate of u if u plus iv is analytic, and if u plus iv is analytic, we have Cauchy-Riemann equations, and we are given function u, so we can obtain partial derivatives of function u, and we will obtain Cauchy-Riemann equations we will obtain partial derivatives of harmonic conjugate, and by doing integration of either 1 or 2 we are able to obtain required harmonic conjugate. So in this way we have obtained the harmonic conjugate of given function, and we will continue with this type of problems in upcoming lectures. Thanks for watching.